All right, guys. So today we're going to get a little more detail into simulation. And unfortunately, simulation kind of is it's going to take a little creativity. So I'm going to give you sort of a general way to design a simulation, some guidelines to kind of follow, and then show you a couple of examples of a full simulation, and then have you guys look at some descriptions of simulations and talk about what's wrong with them, if anything. So our first simulation is going to be a pretty standard one. So here's sort of the situation. So it says, design a simulation for the following. Cheerios is doing a promotion where inside each box of cereal there is one of three prizes: a bee figurine, a fidget spinner, or a small coloring book. GM, who makes Cheerios, reports that 20% of boxes contain fidget spinners, 30% contain the coloring book, and 50% contain the little bee figurine. Excuse me. And then it says, about how many boxes would it take a person to collect all three prizes? So mathematically, we're going to solve this not using formulas or anything like this. We're actually going to design a simulation to model choosing bee figurines, or not bee figurines, but boxes of Cheerios, and seeing how many boxes of Cheerios it would take us to get all three prizes. So here's the first thing I would kind of go with. And I've already written this out because, as you're going to see, it's a lot of writing. So if you want to kind of copy, if you're watching this by yourself, if you want to kind of copy everything down first and then go back and actually listen, that might be a really effective way to look at this. Or you can copy it down and read it, or follow along as we go. So the first thing I'm going to try to explain when I am talking about my simulation, and by the way, this is totally fair game for the AP exam. You could be asked to describe a simulation, and if you are, you pretty much need to be as detailed as I'm about to be. So the first thing you need to talk about is, what question am I answering? So to look at that, I'm going to look at the very last question they asked, which is about how many boxes would it take a person to collect all three prizes. So they want a number. They want to know how many boxes on average would it take, or they didn't say on average, but I'm adding that in. How many boxes would it take to get all three prizes? So I'm going to actually write that question down so that I am clear about what it is that I'm going to be simulating, which goes into our next question. So the next part I'm going to talk about is what action exactly is being simulated. So in the description above, what is it that I am modeling? In the example you guys kind of messed with in the last lesson, the action you were modeling was having a baby. In this case, you are going to simulate buying a box of Cheerios. That is the action that's going to be simulated. So we will simulate buying a box of Cheerios and checking which prizes is inside. That is the action that will be simulated. So that's the second thing you're going to want to address. Next, and this is kind of the long part, how will I model the outcome of this action? So, okay, that's the action I'm going to simulate. How am I going to actually model the outcome of this action? Before, when we were flipping coins to get boys or girls, the way that I modeled having a baby and ending up with a boy or a girl was the act of flipping a coin. In this case, this is a little more detailed than just, hey, you're having kids, it could be a boy or a girl. There's more than two outcomes, and each of the three outcomes that are possible are not equally likely. You have a fidget spinner that's got a 20% chance of showing up. You got 30% chance of getting a coloring book and 50% chance of getting a bee. So because of that, we're going to get a little creative, and we're going to be using random numbers. So just like in the last unit, we looked at random number tables and we looked at random number generators. In this unit, you could also use either one as well. So in this case, for this particular example, just for easiness, we're going to use a random number generator on your calculator. So here's sort of where we're going with this. And by the way, everything I'm writing here you would actually also have to write in your description. So here's what I'm going for. So since there's a 20% chance, 20 out of 100, literally, of a fidget spinner, 30% chance of a coloring book, and 50% chance of a bee, we are going to use the numbers 1 through 100 to represent getting each prize. And so what I'm going to do is I'm going to pick a bunch of numbers, random numbers between 1 and 100, and I'm going to have numbers 1 through 20 represent getting a fidget spinner, because that is literally 20 numbers out of 100. So that should match the probability of getting a fidget spinner in the first place. So, I don't know how that happened. Okay. So, because there's a 20% chance of getting a fidget spinner, I'm going to have numbers 1 through 20 represent getting a fidget spinner. Next, I'm going to have numbers 21 through 50 represent getting a coloring book. So if I land on any number between 21 and 50, there are 30 of those numbers, hence the 30% chance of getting a coloring book. And then if I land on numbers 51 through 100, that's going to represent getting a bee figurine. So that's just how I'm going to choose to do this. I'm looking at random numbers between 1 and 100, and 20 numbers represent fidget spinner, 30 numbers represent coloring book, and then 50 numbers represent getting a bee figurine. Now, I chose the numbers 1 through 100. You could have chosen any numbers that also equate to 20%, 30%, and 50%. So for example, you could use numbers 1 through 10, and 1 and 2 would represent the fidget spinner, 3, 4, and 5 would represent the coloring book, and 6 through 10 could represent the bee. That's perfectly fine too. There's many ways to do this. However, for me, whenever we're talking percents, I like to use numbers between 1 and 100 just because it's clear, it's easy, there's no way for me to screw this up, basically. So that's how I'm going to model the outcome of this action. So those numbers are going to represent me buying a cereal box and getting a prize in that cereal box. So I say what the numbers represent, and then I'm going to say we will use our calculator's random number generator to select a number that's going to represent picking a cereal box at random. Okay? So that is the whole description of how I'm going to model this action. If I was looking at the simulation for having kids, I would say I will flip a coin. Landing on heads will represent having a girl, and landing on tails will represent having a boy. That is all I would need to say for that particular simulation. So that's sort of this section of your description of your simulation. Okay. Next, you need to be clear on what is going to constitute one trial. Because we, in a simulation, are going to perform multiple trials. So, for example, when we were going through and trying to simulate having a boy or a girl, you didn't just flip a coin one time and that was it. You flipped a coin multiple times because there were multiple kids you were having. So in this case, what constitutes one trial? So in this case, one trial will be selecting random numbers until we have all 3 prizes and counting the number of, quote, boxes it takes to get all 3 prizes. So I'm going to keep pressing the random number generator until I get all 3 prizes. So until I get 3 numbers in each of these ranges. So that's going to count as one trial. Next, and this is completely up to me unless the problem says otherwise, it says how many trials will be performed. I mean, the more the better. The more trials you have, the more accurate your result is going to be. But we're lazy and we don't want to do a ton of trials. So, okay, what's the minimally accepted number of trials? Usually it's 5. So in this case, we're going to repeat this process for 5 trials. Okay? And then finally, what will be recorded when we are finished? So, all right, how many times are you going to do this? That's cool. What are you actually going to record when you're done? So in this case, we're going to take an average number of boxes it takes to get all 3 prizes. So in trial number 1, I'm going to get a specific number of boxes. So maybe it's going to take me 10 boxes to get all 3 prizes. So 10 would be the number I record for trial 1. And then I'm going to do trials 2, 3, 4, and 5. I'm going to get different numbers for different trials. And in the end, I should end up with 5 different numbers of boxes. Well, I want to get an average of those to give me an idea of, hey, on average, how many boxes will it take to get all 3 prizes? And by the way, whatever you're recording when you're finished should answer the question that you started your simulation with, okay? So again, if you need to pause this at any point to actually scribble all this down, go ahead and do that. But we're going to actually now look at what this would look like. So for trial number 1, and you guys all, I'm not going to have you standardize this. So you guys all have different calculators. You're going to potentially get different random numbers when you generate them. So for my particular set of random numbers, for my trial number 1, I got 94. That would count as the B because it's between 51 and 100. 11, fidget spinner. 1, fidget spinner. 55, another B. 86, another B. 98, another B. And then finally I got 28, which is the coloring book. So for me, for trial number 1, it took me 1, 2, 3, 4, 5, 6, 7 boxes to get all 3 prizes. So that's trial number 1. I'm not going to show you the exact numbers I got, but for trial number 2, it took 4 boxes. For trial number 3, it also took 4 boxes. And hey, for trial number 4, it took 4 boxes. And then for the last trial, number 5, it took me again 7 boxes. So for me personally, that is how this simulation took place. Now, if you guys want to try this on your own, you will most likely not get the same number of boxes that I did. That's totally fine because this is a simulation and it's dependent on your calculator and we're not standardizing the random numbers we get. Then you guys might have a totally different average than I would if you did this on your own. However, if I take my average, add them all up, divide by 5, I get 5.8. So in answer to my question, it takes about 5.8 boxes on average to get all 3 prizes, according to this simulation. Okay? So the main thing is to make sure when you describe your simulation, you answer all of the questions that I have on the side here. So first, what question is it that I'm actually answering? What action is being simulated? How will I model the outcome of this action? What constitutes as one trial? How many trials are you going to do? And what are you recording when you're done? Okay. So that is sort of the first example. Please feel free to pause this, take it in, watch it again, look at it. But we're going to go ahead and move on to a second type of simulation that's a little different. Okay. So moving on, we have simulation number 2. And this is a similar problem for what you would see in your homework. So you're going to read kind of the same idea and then we'll talk about what they're actually asking for. So again, it says design a simulation for the following. So it says researchers recruited 20 volunteers, 8 men and 12 women, to take part in an experiment. They randomly assigned the subjects into 2 groups of 10 people each. To their surprise, 6 out of the 8 men were assigned to the same group. Should they be surprised? Design and carry out a simulation to estimate the probability that random assignment puts 6 or more men in the same group. Follow the 4-step process. The 4-step process is something, the textbook that I have you guys use, that's what your homework copies are from. The 4-step process is actually something that we are going to save for the second semester. And so ignore that. So when you are actually reading your homework, when it says 4-step process, ignore that completely. Instead, what you're going to do is when you write your simulation, you're going to reference essentially the questions we asked in the first simulation. So the first thing we're going to do is, okay, they've just described what they want you to simulate. So the first question you're going to answer is, what is it that they want you to simulate? So what are they looking for? And I said, we want to find the probability that 6 or more men end up in the same group. Very simple, refers back to the prompt. Done. Next, what action am I going to simulate? Okay, well, I'm picking people from these 20 volunteers and splitting them into 2 groups of 10. So we will simulate randomly assigning these 20 volunteers into 2 groups of 10. for the sake of variety, so that you see a different type of problem, in this problem we're going to use a random number table. You could totally use a random number generator on a calculator. That's absolutely fine. You could put fake names in a hat and pick them. That's absolutely fine. But as we're going to actually do this, since it says design and carry out a simulation, we're going to use a random number table, okay? So if you have that random number table, you may want to take it out. So here we go. So next, okay, what am I finding? What action am I simulating? How am I going to model the outcome of this action? Well, since I'm using a random number table, I need to be clear on what numbers represent what and choosing numbers and what that means. So essentially what's going to happen is choosing numbers on a random number table is how I'm going to model picking 20 volunteers for this group of 10. So I have here, it says digits 00 through 39 will represent selecting a man, and 40 through 49 will represent selecting a woman. That 49, I'm pretty sure, is not supposed to be 49. Pause. 99. Yeah, I thought so. Okay. JK. Hold your horses. There we go. That's a, wow, that's not what I wanted. Okay, that's a 9. Sorry, guys. It's like 49. That's wrong. Okay. So let's talk about where that comes from. Okay. So in this group, there are 20 people, and 8 of them, oh, that got cut off too. 8 of them are men. And if I take 8 out of 20, whoops. If I take 8 out of 20, that actually is 40%. And so since I'm dealing with 40%, again, what I'm going to do is I'm going to look at numbers. I'm going to look at a total of 100 numbers. And I would like 40 of those 100 numbers to represent men, since 40% of my sample are men. So you may remember on a random number table, rather than looking at numbers 1 through 100, if I do that, if I use numbers 1 through 100, I have to look at digits 3 at a time, because 100 has 3 digits, and I don't want to do that. So instead, I'm going to look at numbers from 0 to 99. There's still 100 numbers there. And then I get to look at digits 2 at a time, and I actually get to use all of the numbers that I pick. So I'm going to let numbers 0 through 39 represent selecting a man, because there are 40 of those numbers, and 40% of my sample should be men. And then 40 through 99 will represent selecting a woman, and for the same reason, 60% comes from, that's 12 out of 20. So 12 out of 20 of my sample is women, that's 60%. So these 60 numbers, 40 through 99, will represent selecting a woman. So I have now said, okay, I'm going to pick random numbers using a random number table. Digits 0 through 39 will represent selecting a man. 40 through 99 are going to represent selecting a woman. So, using a random number table, we're going to choose digits 2 at a time to represent a number. Okay. To represent a person, actually. A volunteer. Timeout. To represent choosing a volunteer. There. That's clear, right? So this is represent choosing a volunteer. We will choose 10 numbers and count how many men are in the group. If the group has at least 6 men, then we will write yes. And if not, we will write no. Okay, so one more time just to clarify. So using a random number table, we're going to pick digits 2 at a time to represent choosing a volunteer, or choosing volunteers. We will choose 10 numbers and count how many men, quote unquote, are in that group of 10. So if the group of 10 has at least 6 men, that's what we're looking for. We're looking for the probability that we have 6 or more men in the same group. And if that is the case, we're going to write yes. And if not, we're going to write no. Okay, well, altogether that counts as 1 trial. We're going to conduct 5 total trials, again, because 5 is sort of our minimum accepted. So I've said this is one trial. This thing is what counts for one trial. We're going to conduct 5 trials. And in the end, what are we going to actually write down? Well, in the end, we're going to count how many yeses we have out of 5. So for example, if I take 5 different groups and 2 out of my 5 groups did have at least 6 men, then that percentage, 2 out of 5 or 40%, is going to be the probability I'm looking for. So count how many yeses, responses we have out of 5. This percentage will be the probability that 6 or more men end up in the same group. Okay, so that is the entire description of my simulation. And now they wanted you to actually carry out the simulation. So I'm going to show you what I got using the random number table. Now, it didn't tell you what line to use specifically. On some of your homework questions, it would. On the AP test, if you're asked to do this, they would probably give you a few lines of a random number table and just make you use those. So again, please feel free to pause this and catch up. But here is what I got. So looking at my lines in the random number table, this is sort of the first group that I had. So the first line that I was looking at was 19, 22, 39. So those are the first numbers I have. So 19 counts as 19, that is a male. 22, man. 39, man. 50, woman, so I'm not going to circle it. 34 is a man again. Okay, so far I have 4 men. 57 is a woman, 56 is a woman, 28 is a man, 71 is a woman, and 32 is a man. So in this case, I chose 10 total numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And out of 10, there were 6 that counted as males because they were between 0 and 39. So my first trial, I actually am going to record a yes. Then I'm going to go through and continue looking at the random number table. I chose 10 numbers from each of the following, and as you can see, in the rest of my trials, in trial 2, 3, 4, and 5, I did not get at least 6 men in any group. In fact, it looks like I got 3 men for trial 2, I got 3 men for trial 3, I got 2 men for trial 4, and then again 3 men in trial 5. So in this case, on my first trial, I did get 6 men, and on the rest of them, I did not get 6 men at all. So in this case, I had 1 yes out of 5 total trials, which is approximately 20%. So that 1 out of 5, that 20%, is the probability that I'm looking for. So I'm going to say, according to this simulation, the probability of having 6 or more men in the same group is 20%. Okay. I would encourage you, just because this would help you to actually do this, I would encourage you to pick a line on the random number table and do the 5 trials yourself and see what you get. By the way, it is perfectly possible that you would get all 5 of these no. So you could do this 5 different times and in none of the trials have 6 or more men. And if that's the case, then it would be 0 yeses out of 5, which would be 0% probability. That's perfectly acceptable. So I would encourage you to actually go through and do this yourself so that you kind of understand the process and understand how it works. The more you actually do this process, the easier it'll be to describe, because you're describing what you actually had to physically do. Okay. So those are 2 examples of simulations that you have to describe and carry out. On the very last page of these notes, there are 2 examples where, and parts A and B of each, where they describe a simulation, and you are asked to talk about what's wrong with them, if anything. So I would like you guys to, when you're finished writing all of this and chewing on it and thinking about it, I would like you guys to look at the examples on the next page, pause the video, and try to see if you can figure out what's wrong with each of them. I believe one of them actually is perfectly a valid design, but the other ones are not. So go through, read through each of them, try to figure out what's wrong, pause the video, and then when you're ready, you can check out the answers to each. Okay? All right, so let's see how you did. So our first example, number 1, it says, explain what's wrong with each of these simulation designs. So it says, according to the Center for Disease Control and Prevention, about 36% of U.S. adults were obese in 2012. To simulate choosing 8 adults at random and seeing how many are obese, we could use 2 digits. Let 0 to 35 represent being obese, and 36 to 99 represent not being obese. Move across a row at table D 2 digits at a time until you find 8 distinct numbers. No repeats. Record the number of obese people. Okay. So that is interesting because I read that at first and I think I don't get it. What's wrong with it? So let's check some obvious situations here. So first of all, they tell you 36% of US adults are obese. A major error that people make is the numbers they pick to simulate being obese don't match the actual percentage. So let's check that. 0 to 35. Does that accurately represent the 36%? Yes, because 0 to 35, since you're counting 0 to 35 includes 36 numbers out of 100. So that actually perfectly matches the 36%. So let's look at the other set of numbers, 36 to 99. Well, that's just the remaining percentage. That also matches. Okay, so that looks good to me. So I don't quite get what's wrong. Let's keep going. Next, it looks like we're moving across a row in table D. That's your random number table. Let's check the digits they use. They say 2 digits at a time. That's right, because we're looking at 2 digits. The next thing, we're simulating choosing 8 adults. So did they do that until you find 8 distinct numbers? Yes, they did. Okay, Brisa, so what's the problem? Well, in this case, we want to simulate choosing 8 adults and seeing how many are obese. You're recording the number of obese people. I don't get it. This is your issue. No repeats. So here's the deal. We're picking a sample of 8 people, but it's not like they told us, hey, out of 100 people, exactly 36 of them are obese. Like, here are their names. Frank, Janet, Frederick, they're all obese. Now pick 8 of them. How many are obese? So they didn't do that. Instead, they just gave us a blanketed 36% of US adults are obese. And so in this case, actually, we would include repeats. That would be okay because the people we're picking, quote unquote, do not actually represent human beings per se. So yeah, we're choosing 8 adults at random, but the 8 adults we're picking don't necessarily have personalities, if you will. So it's not like I'm picking like person A, person B, person C. I'm simply picking obese or not obese, essentially. And so that 36% is modeled by the 0 to 35. And so when I'm picking 8 numbers at random, I can include repeats. That's totally fine. So if I got 34, that doesn't mean I'm looking at the same obese person. It just means that I got a person who is obese, and then I got another person who is obese again. So in this case, because they started with a percentage instead of starting with an actual list of people, I actually do want to include repeats. Now, if they gave me a list of people, like here are 100 human beings, here are their names, here's how many of them are obese or which ones are obese, that is different. So if I have 100 people and I'm picking a group of 8 from that 100 people, that is different. Then you do want to make sure there's no repeats. But in this case, they just gave you a blanketed percent. That's your issue. So all you would really have to say for this is this simulation should include repeats because you're not collecting a unique group of things or people. You're just using the percentage. You're just estimating a percentage. All right. So we move on to part B. So let's see how you did there. Assume that the probability of a newborn being a boy is 0.5. To simulate choosing a random sample of 9 babies who were born in a local hospital today and observing their gender, use one digit, do randint 0 through 9 on your calculator to determine how many babies in the sample are male. Okay, so we got some problems here. So first of all, we didn't mention which numbers represented each gender, so that is a problem. We also didn't mention how many random numbers we should actually choose. Like, we're looking at numbers 0 through 9, but I don't know if 0 through 5 represent being a boy. I don't know if 0 through 4 represent being a boy. So in this case, this simulation description just doesn't give enough detail. So if you mentioned the problem didn't say which numbers represented which gender, that's great. If you said there was no mention of how many numbers to pick, that's great. If you mentioned picking 0 through 9, 10 numbers, what does that even mean? We're looking at 9 babies, that doesn't match. That's fine because they didn't really tell you what they were doing exactly. So that's your issue with part B, okay? So we're gonna move on. So if you haven't done number 2 yet, do number 2 and then check it out. All right. So number 2, in this case, determine whether each of the following simulation designs is valid. Justify your answer. Okay, let's see what we got. So it says, according to a recent survey, 50% of people aged 13 or older in the United States are addicted to texting. Okay. To simulate choosing a random sample of 20 people in this population and seeing how many of them are addicted to texting, use a deck of cards. Shuffle the deck well, and then draw one card at a time. A red card means that a person is addicted to texting. A black card means he isn't. Continue until you have drawn 20 cards without replacement for this sample. Okay. So what's wrong with this? Well, let's chat. I want to simulate picking 20 people. I'm picking 20 cards. What is the probability they are addicted to texting? It's 50%. Well, okay. We split up the deck red cards and black cards, and I know that in a standard deck of cards, half of the deck, 50% is red, half of the deck is black. So we're okay there until we get here. What does without replacement mean? It means you're picking cards one at a time and you are not putting those cards back. And so if you are picking cards one at a time and you're not putting those cards back, you got yourself a problem. Because 50% of people in the US, 13 or older, whatever, are addicted to texting, so you need the probability of choosing each card to be 50%. Well, if the first card I pick is red and I don't put it back, then the next probability I have of picking a red card is not 26 out of 52, 50% anymore. It's 25 out of 51, which is not quite 50%. So hopefully you came up with that. Because the cards are not being replaced, the probability will change from trial to trial and will not remain 50%. So this design is not valid. Okay. All right, so we got one last one. Let's see if it works. Okay. So it says a tennis player gets 95% of his serves in play during practice. That is, the ball doesn't go out of bounds. To simulate the player hitting 5 serves, look at 5 pairs of digits going across a row in table D. So it's your random number table. If the number is between 00 and 94, the serve is in. Numbers between 95 and 99 indicate the serve is out. I'm going to try to move this right now. Move this thing down. There we go. Okay. So let's see. So as you can kind of see here, I gave you a little bit of the answer, but let's talk through it. So again, I'm simulating 5 serves. So let's make sure I'm picking 5 numbers. Looks like I am. Look at 5 different pairs. Okay. 95% is the probability I'm given. So that needs to match the numbers that I actually represent with the serve. And it looks like we're good there. 0 to 94 represents, that is 95 total numbers out of 100, which matches with the 95%. And 95 through 99 is 5 numbers, so that represents the 5% that the ball doesn't go, or that the ball goes out of bounds. So the numbers match, the probabilities match. The probabilities aren't going to change from number to number because we're looking at a random number table. You're looking at 5 pairs of digits at a time. This looks pretty good. Now, again, if you notice, I didn't write this, but if you notice, it doesn't mention repeats. And if it doesn't mention repeats, then you include them. Is that okay? Well, yeah, because they just gave you, again, sort of a blanketed percentage. They gave you a percentage probability that's given. They didn't say out of 10 serves, Franklin missed one of them or whatever. They just gave you a percentage. So in this case, it would not be appropriate to skip repeats, and they didn't say skip repeats. They left that out, which they should. So in this case, the design looks pretty good. This is perfectly valid. Okay. Whew. All right, you made it through the marathon. So simulation, that's kind of how this goes. Looking at simulations and commenting on if they're valid or not is sort of the easier part of this. The harder part often is actually coming up with your own simulation. It takes a little bit of creativity. So talk to each other, work together, do your stinking homework, people. It'll really help when it actually comes time for tests and or quizzes, etc. All right, y'all, have a lovely day.